Hello everyone. So in today's simulation, we will talk about hydrodealkylation in membrane reactor. At high temperature and pressure and in the presence of hydrogen, toluene can be demethylated to produce benzene. Therefore, benzene can react reversibly to produce biphenyl. In this example, the simulation of the hydrodealkylation process carried out in a membrane reactor. This reactor arrangement allows for a continuous addition of hydrogen to the process, increasing the selectivity of a desired benzene product. Also, in this lecture, we will modify the predefined plug flow reactor in the reaction engineering interface to set up a membrane reactor model. We will also learn how to create a thermodynamic system from thermodynamics to get different thermodynamic and physical property functions for each compound and their mixture. After coupling all chemical species in the reaction engineering interface to the corresponding species in the thermodynamic system, the required species and the mixture properties are automatically created and added to the property package. So in this model, two important reactions occurs in the thermal hydrodealkylation of toluene. The main reaction involves toluene reacting with hydrogen to produce benzene and methane as shown on your screen. The dealkylation reaction rate is first order in toluene concentration and half order in hydrogen concentration. And this is the rate equation. At the same time, the biphenyl is reversibly formed from benzene. According to this reaction, the rate of coupling reactions follow the mass transfer mass action law according to this relationship. In this expression, the rate constant follows Arrhenius type behavior, and the values of frequency factor and the activation energy in joule per mole are taken from the literature, which is shown in this particular table. The chemical reactions given in equation 1 and equation 2 suggest that maintaining a high concentration of hydrogen would be beneficial to ensure a high benzene yield. Such process condition can be achieved using membrane reactor. As shown in this figure, hydrogen can be supplied continuously across a porous membrane. The species mass balance for hydrogen in the membrane reactor is shown in this relationship, where F is the molar flow rate in the reactor, V is the reactor volume, R is the species rate expression, and F is the molar flow rate for unit volume, shown in SI units, which is mole per cubic meter second across the membrane. The velocity of hydrogen gas across the porous membrane can be described by a Darcy law, which is shown by this expression, where K is proportionality constant, P shell is the gas pressure on the shell side of the membrane, and P reactor the pressure on the reactor side. The molar flow rate per unit volume across the membrane then becomes shown by this expression, where A in the membrane surface area per unit volume and C shell is the concentration of hydrogen on the shell side. Except for hydrogen, the other chemical species in the reactor do not pass through the membrane, and their material balance thus follow a standard plug flow equation as shown here on the screen. The adiabatic energy balance for a reactor is given by this particular expression. In equation 4, C mix represent the mixture reacting system molar heat capacity, and Q represent the heat due to chemical reaction. In this expression, Hj is the heat produced by reaction J, calculated from this equation. In equation 5, Hi represent the species molar partial molar enthalpy, and Vij the stoichiometric coefficient. The last term in the energy balance account for the energy transfer associated with the flow of hydrogen across the membrane as shown here in this equation. So the reaction engineering interface automatically set up and solve and solve setup and solve question 3 and question 4 when you select the predefined plug flow reactor. To adjust the default model to count for a hydrogen entering the reactor through a membrane, the flow term FH2 has to be specified and included in the material balance for hydrogen. Solving the energy balance equation 4 requires the input mixture of molar heat capacity C mix and the partial molar enthalpy HI for the reacting species. In this example, these thermodynamic properties are calculated from the property package. We need to click on model wizard first, and then we need to click on space dimensions, and we need to select the physics. So we need to click on chemical species transport, and then we can click on reaction engineering and click on add. Then we can click on study, and for this particular case we are going to study the stationary plug flow problem. So we need to click on stationary plug flow, and then we can click on done. So the first we need to create a thermodynamic system including the 5 species needed for this model, which are hydrogen, methane, benzene, toluene and biphenyl. So click on reaction engineering, then we can click on thermodynamics and click on thermodynamic system. So a thermodynamic system wizard will appear. So we need to click on the first thing that we need to change is the phases, which are vapor, liquid, equilibrium. Then we can click on next. Here we need to select the components that we are going to use. So the first component that we have here is hydrogen. So we can type hydrogen, and we can add hydrogen. Then similarly we can add methane, and we have benzene, we have toluene, and then finally we have biphenyl. So these are our components. Then we can click on next. We can keep the property package as SRK question of state. Then we can click on finish. So we can see here we have a thermodynamic system has been created, which are vapor liquid system 1. So now we can right click on the vapor liquid system, and we can click on the mixture property. So from the list we need to click on enthalpy, and then click on plus. After you do this, then we can click on the next button here, and here we need to make sure that we have vapor phase selected. Then we can click on next, and here we need to select all of them. So we need to click on add all. After we add all, we can click on next button, and here we can see we have all the information that has been set up, and then we can click on finish. So this is what we have so far. We have added the thermodynamics, and we have changed some information. The first thing I want to change here is the name of the function, which is HF in my case, and I can change this one also, mixture enthalpy of formation 1. Right. So after changing all this information, we can now able to add 2 important information. One is parameters, and second is the variables. For parameters, we need to click on parameter, and we can just scroll down, and we need to select this folder, and we have these parameters inside our folder. So we just select those parameters. the files of these parameters I will provide in the description down below. Right, so these are the parameters. We have the temperature of the inlet, which is shown here, 1200 Kelvin. We have the pressure of the shell side, which is mentioned here. Pressure of the reactor side, we have the value of K and the A. After we add the variables, now we need to add after we add the parameters, now we have to add the component variables. We need to click on the definition on the component side, click on the variable, and in a similar way we can add on this folder and add on the variable. Click on the variable file and just click on open. And these are the variables that we have. We have all the variables. We have some expressions to calculate these variables also. So we have these two set up. Then if you look at in this particular case, this one is looks a bit different. You can see the orange color expression here specifies the molar flow rate of the benzene, which will be defined later in the reaction engineering interface. The reason for this variable expression being orange is that it includes expressions that are not yet defined. Once the expressions are defined in the reaction engineering interface, the orange color will be converted into black unless there is no unit error. Okay, so then we can click on the reaction engineering, and we need to change the reactor type to a plug flow reactor, and we need to select the energy balance, and we need to click on include energy balance. And here we have an expression to calculate this, so we just type that, and we make sure this is a gas phase. And for the pressure we can write P_reactor. So after defining these things, now we need to add reactions. So for reaction, we need to click on reaction number 1, and we can type in the reaction, which is in the first reaction that we need to type in 5CH3 reacting with hydrogen to form benzene plus methane. We can apply this, and we can go down in the reaction rate section, and we need to make sure it is user defined, and this expression we need to change slightly. So we can write here after this the following expression. This should be in a bracket, and that will be written like this. This will be mole per cubic meter. Look close to the power 0.5 times 1 in the units mole cubic meter. Close. If everything is correct, the expression should be black, not yellow. Right, after we do this, we can find out the rate constant, and we can click on use Reynolds equation. For the frequency factor, we have the values from the literature, that is 5.67 e to the 9, and for activation energy we have the values from the literature, that is 228.2 e to the 3 joule per mole. Right, So this is how we define the first reaction. Now let's talk about the second reaction. So we can click on second reaction. In the second reaction we need to type in the formula, which is the the reaction, that is C6 and since it is 2A, so C12 H10 plus hydrogen, and then we can apply this one. And for this we need to click on run this equation, and for frequency factor for the forward reaction we can put 1e to the 8. For frequency energy, activation energy for the forward is 167.5 e to the 3, and for reverse frequency factor we have 1 e to the 8, and activation energy is 149.8 e to the 3. So after you key in all this information, you need to do one more thing, that is additional source. You need to add some additional information. For this you need to click on additional source, and for this additional source we need to look at the volumetric property of hydrogen, and here we can key in F hydrogen. So this is the information that we need to put as an additional source. Okay, then we can click on the initial values. We need to provide the initial values. For the initial values we have the temperature of the inlet, that is already been defined in the parameter section, so we need to go into that expression. And for the initial values we need to have 10 molar flow rate and then we have a 10 molar flow rate for hydrogen. So these are the initial values that is mentioned. Then click on the model and reaction engineering. Then we need to click on the thermodynamics in the mixture property, and then we can go down and we need to ally the species with the thermodynamic value. So for example, the first one has to be matched up and then we have this one matched up, then we have this one matched up, we have methane that is matched up, then we have the hydrogen. So after we do all this, now we need to go for the study part. So in the study part we need to click on the study, and the first thing that we need to see in the study, we need to rename the study, and we need to write here tubular reactor, and then click on OK. And then the stationary window, we need to we need to expand the node, and here we can see we have the reactor volume. This total volume is 1 cubic meter, and what else we have? We have the physics section. In the physics section we click on the modify, and then we need to make sure the first part we need to disable the additional source. Once we disable it, then we can click on compute, and we will wait for the process to finish. And now you can see from here we have the graphics which is shown up here. So if you look at these graphics, you can clearly have an idea, if you are using a tubular reactor, then how the reaction proceeds from the beginning to the end. So in this simulation, the reactor is assumed to be a standard tubular reactor, that is without hydrogen entering through the reactor's circumference. The reactor is fed with the equimolar flow, which is 10 mole per second of hydrogen and toluene. At the inlet, the reactant gas is held at 1200 Kelvin and 2 atmospheric. The results are shown here on the screen. You can see here on this particular part the results. Now let's move on, because we want to see the temperature distribution as well. So this is only showing you the first, which is the molar flow rate, and we need to change some information here according to our plot. So how we can change the information? If you look at here, so we need to right click on the molar flow rate, and we need to rename this, and we need to define this as concentration and temperature profile for a tubular reactor. And then press OK. Look at now we can find out the plot setting here on this side. And on the plot setting, the y-axis we can type here. On the y-axis we can type here concentration. And for the units, we need to write here mole per cubic meter, which we should write in this fashion. Right, you can see here it is written now. Right, now we need to select the two y-axis. We need to go down in the legend section, and we need to make sure we need to change this information on this side. So yeah, we can able to see what is happening. So this should be in upper left. After you change this one, we need to add a temperature. So we need to click on global, and then we can rename this global, and we can choose rename. We can write here concentration, and then press OK. Alright, so in the setting window for the Y data, we can just clear all, and then we can type in the following information here. .1 C6 H5 CH3. You can copy this and paste it multiple times. Second one is hydrogen, and then we have benzene, and then we have methane, and finally we have our H10. Right. So after providing this information, can go down, we can select the coloring and style section, and here we need to change the width to 2, and in the legend section we need to select that one and change from manual to automatic to manual. Right, so after we put this one, we need to change this to your names. So this one is called toluene, that is hydrogen, that is benzene, that is methane, and finally we have biphenyl. Right, then we need to click on this concentration and temperature. Right click and click on global. In here we need to first change the name of the global to temperature, and then we need to click here and to change that. First thing is we need to change this to temperature, that is change. Then we need to click on expression, and we need to go to reaction engineering, and we need to click on temperature. So this is now change. Then we need to select we can click on plot on secondary axis. Checkbox is click. We can go down to coloring, and we can change the width to 2, and we need to click on show legend, and here we click on manual, and here we need to type in temperature. Then we can click on plot. After we click on plot, you can see now we have both the concentration and the temperature on the same plot. Right, so this is how we can simulate the tubular reactor for this particular example. And now we can switch to a membrane reactor. So for this we need to add a study. So to add a study, we need to click on home, and we need to click on add study, and we have this add study which is shown up here. So in this add study we need to click on add study option. Then we need to click on stationary plug flow, and we need to click on plus add study, and from the home button we already have the add study added here. So we need to right click on this study, and then we need to change this into membrane reactor. Membrane reactor, press OK, and then from the we have a data section. Okay, and then we can see that we have a membrane reactor that is added here, the name. Then we need to click on, we're going to see this option here, which is the first one. We need to uncheck, and we need to make sure, and we already make sure that in here we have additional sources that is being selected. Click on compute. So once we compute, you see here, then we need to see the results. So for the results we need to click on the concentration profile, and we can click on duplicate. For the duplicate part, we need to change the name. Right click and change the name to membrane reactor. So this is our membrane reactor. Click on OK. Then we need to find out the concentration membrane reactor. We need to go on this and find out where in the data section we have this option selected, and we need to choose membrane reactor. Okay, here we need to choose membrane reactor, and then we can see everything else is okay. Then we need to click on plot. Once we click on plot, you can see a slight changes in the plot, and this basically suggests that if we use membrane reactor, the membrane reactor with a continuous supply of hydrogen through membrane, this figure shows that concentration distribution. Clearly the membrane reactor produces benzene with great selectivity. So this is the end of today's simulation. I hope you have a good idea about how you can able to simulate the membrane reactor and the tubular reactor inside COMSOL. Thank you so much for listening and watching this video. Please like, share and subscribe, and I can see you in the next video. Thank you. Bye.